So, I want to go over, just kind of summarize the quantum recipe, kind of connect things, hopefully, a little bit to think about the things we measure and then how we sort of mathematize that in the form of quantum mechanics. It's really just a summary of all the little bits that we've seen. And then I will pause the recording and start a new one. And then in that, I want to discuss the Einstein-Podolsky-Rosen paradox, the EPR paradox. And then, if we have energy, do Bell's theorem. We'll see how that goes. So hopefully, the goal is to have these in 3 videos so that they're not so large to take in at one time. Okay, so let's kind of review or summarize SUM.
Another M.
Yeah, I need another M. There you go. Summarize quantum mechanics. All right, well, let's start by, I mean, it's so bizarre. If you read about this in kind of advanced quantum mechanics books, they start with a list of postulates, and it's fine, but you totally lose the context and the motivation. So let's kind of go through and think about what we've discussed. There are systems, evidently. Just we deduce that there are such a thing as a system, I don't even call it an object, but some sort of elemental. I'm just coming up with different euphemisms for something that I don't have a really good word for. Some sort of elemental construct that we can interact with and probe. And when these elemental systems are very small and we're very large, then the rules seem to be a little bit puzzling. We see that, first of all, we see that outcomes of experiments are irreducibly statistical. So there seems to be, and by seems to be, I really mean, it's so well established that it really just, we can almost say it is, as well as we can say anything is in quantum mechanics, that, or in quantum mechanics, in nature, in science. It just seems that the kind of fundamental nature of reality has an irreducible statistical character. And so, and it doesn't seem to be, so one of the questions will be, is this statistical character or a probabilistic nature a probability of ignorance, or is it just a fundamental sort of probability, in which case it would represent something new to human understanding, right? Because all other notions of statistics and probabilities are probabilities of ignorance, and so that's going to be the real question with the EPR paradox and then Bell's theorem. I mean, that's kind of what it's getting at. Okay, so there's a statistical character. We note also that for macroscopic objects, you do various experiments, and you kind of always get lumpy answers. And then there are times where in quantum mechanics, the outcomes are discrete when they wouldn't have been for the analogous macroscopic system. So there's some sort of, that's the quantization part. So there's some sort of discreteness that comes into all this. Okay, so you can interact with the systems, you do experiments, and you see these discrete, random but discrete outcomes. And so what we do is we're going to kind of need to mathematize that. And by looking at the way that to combine different experiments, we deduce that the following kind of construct works. One, we can, we really, because of the randomness, we can run into problems when we say that something an attribute, or that the system is, or that it has some attribute, what I prefer to say is that we can put systems in 100% correlation with certain experimental outcomes, okay? And so I'm going to say that we can define a quantum state, so we can describe a system with a quantum, or with a, or I'll just say a state vector and generically, I suppose going back to Schrodinger, we would write this using Dirac notation. It's a ket psi, and okay, and what this would indicate is that if you could come up with an experiment to measure psi-ness, whatever that means, that would return the value psi. Okay, that's what you would mean by that. So a more concrete example might be if you could correlate a system with a position, like right here, x, then what that means is that if you measure x, you would find, you measure the position, you would find that the system is here 100% of the time. So this, so for example, and usually when you think about specific measurements or observables, you go ahead and label the state according to the correlation implied. So I would say x will, this system described by this state will, or implies, I should say, the system would be measured to be at x, the position x, 100%. Probability, with 100% probability. Okay, so that's what we mean by, no, that's what I mean by a state vector. I'll come back to that in a minute. But the vector part. Okay, so we're talking about correlations with possible experimental processes. Okay, when I say that it's a vector, I mean that, and that really, we saw that was deducible from combining different measurements and looking at different possible outcomes, and I described the experimental results, and we deduced that, and then we described it, I postulated it, and then we showed that these postulates or these rules will reproduce the experimental results. That's really all the sort of derivation you can give it, because science is empirical. So we're kind of looking at the outcomes of measurements and then deducing the rules. So, okay, so what does it mean if it's a vector? We can do all sorts of vector types of things. We can do, yes. So we can do things like, we can form superpositions. Okay, so which just means take linear combinations. So I can take a state psi, and I can say, oh, that's some combination of, position x equals 1 meter plus position equals 2 meters. Right? If each possible outcome represents a vector, and it's a vector, but vectors can be added, then there's got to be some meaning to this. And, well, okay. So what would we mean with this? What we will mean with this is this means that it's equally correlated with both outcomes. So it's not really this or this. It's neither. It's something else which happens to be equally correlated with both. Okay? So, again, don't think about these labels as saying that it is, the particle is here. You should say it's correlated with attributes. And this question of what things are, like what is going on, the isness, is a little bit tricky. You have to kind of train yourself to phrase things in the right way. Okay, so you can form linear combinations, meaning that it would be equally correlated in this case. Okay, okay, so let's kind of pull out the correlations more explicitly. All right, I said that experiments were statistical and out in nature. What we will do, it's not just, so the way that we will describe that in this language is to say not only are systems described by state vectors, these aren't just vectors, these are vectors in an inner product space. And so, and what we will say is, first of all, systems, the state vectors will need to be physical, they must be unit vectors. Right? And if you're going to talk about the length of a vector, then that means there's a norm, sort of a notion of dot product, and in this case it means you multiply by a bra vector, take the inner product, okay? And when we want to talk about probabilities and statistical features, what we will say is the probability of property, let me call chi, given given that the system started out or was prepared in correlation with a property psi, so you can see I slipped. I said correlated with measurement of a property psi, and I just wrote it a property psi. Well, right, so that's kind of the slippery language here, and I'm just being lazy by not writing it all out. But if you have to add all these prepositional phrases, it just grows and grows and grows. So the probability of chi given a property psi is measured by the inner product squared. Probability chi given psi, so a conditional probability. This is the inner product of chi with psi magnitude squared. Okay, so systems are described by state vectors, which indicate correlations with possible measurements. And then if you prepare it in some way, 100% correlated with some property psi, and then you ask what's the probability of a later measurement producing a result of chi, you take the inner product magnitude squared. And that's kind of our recipe for predicting them. The inner product is called the probability amplitude in the language of Feynman. And Feynman kind of, we went through how you could sum over, you have to distinguish between potential results and experimentally amplified results, and there's a calculus of how you take in all the contributions for all the potential unmeasured results and how they contribute to the predicted results to amplified measured results.
Is that path integrals?
path integrals is what you get when you take that to the kind of logical end. So with the two slit experiment, so that was a situation where we had this. And we said, oh, well, take it from here to here, you would add in contributions through two paths. Whoa. Right? And then, but then you could also subdivide it and differently. So that was one example. But let's look at something simpler. We would have just said, oh, we just wrote down the amplitude to go from here to here. But what you could do is imagine, instead of two slits, imagine kind of infinite slits. Okay? So instead of drawing, I'm going to draw dots for the gaps instead of the openings. So just imagine now I've got infinite slits. You could think about the operation going from here to here as it has to pass through an infinite slit situation. Yeah? So let's say it does that. You add up all those. And then you could subdivide that by an infinite times, and an infinite times. And then by doing an infinite number of slits, that's the same as doing no slit, because it's completely wide open, but you think of it as that. So the path integral is the kind of logical extreme where you slice it arbitrary many times in arbitrary many ways.
But how do you do them?
We wrote down the amplitude to go from any 2 points. You just go through, you just have to, we kind of have all the formulas, you just have to go through the process using the things that we have. What will also happen, normally it would be impossible. You would think, well, there's no chance. Fortunately, when you go through it using the formulas we saw, the actual math is that the amplitude to go from one spot to the other in a certain amount of time is given by, it's the, like a bell curve distribution, e to the x squared, turns out. And then when you kind of sum over the unmeasured intermediate ones, you're doing Gaussian integrals. And it turns out, when you understand what you're doing, the output of doing one slice is another Gaussian integral, and then the next slice gives you another. You can just nest them, and so it turns out it's a miracle. It seems you can actually do it. It's all in the phrasing of the problem too. But anyways, it's fortunate that it works out mathematically. It's very possible. In fact, that's for free particle.
It wouldn't work out. That's the.
So for a free particle, you can do it. Once you add interactions, you can't do it exactly, except for very extreme cases, and usually you use some other logic to get it. You can't do it directly, and you have to use approximation schemes. Yeah. So that's a Feynman path integral. That's kind of taking Feynman's calculus rules for amplitudes to their kind of logical extreme. Maybe after we finish this, I can kind of give you a summary, kind of how that goes. It's neat, it's fun to kind of see and think about. All right, so these are our rules for probabilities of vectors. All right, what we saw then, okay, so now let's kind of combine. Let's come back to the superpositions of vectors. So I'm going to switch, instead of thinking about positions, I'm going to think about spins, just because they're discrete and I don't have to worry about, I can do sums instead of integrals here. So let's think about this. If we have a state, psi, and let's just say it's some random combination of, just make a superposition, A, and we'll say this is plus Z in our notation, plus B, plus, or minus Z. Okay, so this is just some random vector in the space. The only constraint is that it has magnitude 1. That means that we have to impose the magnitude of A squared plus the magnitude of B squared equal 1. That's so that it's a unit vector. That's the only constraint. right? Now, how do we interpret this thing? Well, I kind of already showed my cards. I said that we're going to interpret this as being not, it's not going to be really plus z or minus z. It's somehow correlated with both of them. The way we're going to measure that is to take inner products. So given that you could prepare a system in this way, I would say the probability of getting plus z, given that it was prepared in a state psi, is I would take the inner product with plus z magnitude squared, and what you would see using the inner products that we've seen, when you take the dot product with plus z, this one survives, actually just this coefficient survives. This one is gone because it's orthogonal, and this will just give you magnitude of a squared because I have to do the square of it. Similarly, so this coefficient gives me the probability, or it tells me how psi is correlated with a plus z result, the magnitude squared of this coefficient. And similarly, the magnitude squared of b tells me how psi is correlated with producing the result of minus z if you perform an experiment. So that's the interpretation of that. Okay, so we have, all right. Now, any questions? Sorry, the wind's blowing the door, but questions on that, okay? Now, let's come to collapse postulate. So, if we had, I should have kept my state. If I start, so collapse. Okay. If we were to have a state psi given by A plus Z plus B minus Z. Okay, so before performing the experiment, what I'm saying is there's a system, it's in some state, it's correlated in this way with, if I have a choice of measurements to make, I can measure, so let's say I measure spin in the z direction, and I know the results can be plus or minus, and the probability of getting plus would be magnitude a squared, probability of getting minus would be magnitude of b squared. Fine. But we saw when you do repeated measurements that after so it starts out as kind of, you measure spin z, some are going to go one way, some are going to go the other. So, but then after, so we have these streams of particles and they would kind of filter. After let's say you measure spin z, and let's say you would find plus z with probability a squared. Okay? So there you go. And then you make another measurement on the same particle, or same system, I keep saying particle, same system. Future measurements will return plus z 100% of the time, as long as you don't do anything else to disturb it. So if all you do is just keep repeatedly making the same measurements, subsequent measurements produce the same result 100% of the time. So the way we think of that is as follows, or think about it, but the language that gets used is the act of measurement. The first measurement, so the system is neither in plus z nor minus z. I'm kind of stating my answer to the EPR paradox and Bell's theorem. I'm showing my cards there. But I'm kind of showing you which way I'm going to go with it. But that's okay. The original state wasn't this or this. It was correlated with both. And then after measurement, okay, so you make a measurement. after the measurement, you find either plus z or minus z, one or the other. You measure spin z, you don't ever see half of this, half of the other. It's one or the other. Okay, it'll be here or here. And then further measurements, these two it's robust under further measurements. So it stays plus z, or this one would stay minus z. Okay, so after you make this measurement, in all ways, the system behaves as if it truly is described by a new state vector, which is given by plus z or minus z. So what we say is that this original wave function, after being measured, has collapsed to this wave function.
Is it universally thought of as like the collapse of the wave function, or about the people that think it like branches off and?
Yeah. So there are other ways to think of it where, so there are people who, in the many worlds interpretation, you say that it is, instead of saying that it's neither of these, they'll say it is, right, like in a fundamental, as an element of reality. It really is this and this in some sort of a weighted way. And what they would mean, I guess, is like the number of branches where it's this value. So they would think about the universe as like a many-fingered structure. And I guess what you're going to say is something like the fraction of paths or scenarios where it has one value is A, and the fraction where the other value is B. I'm not an expert in thinking about things that way. And then what they would say is there is no, when you make, what really is, they would say there is no measure, there's no collapse in that case.
It branches off and you're seeing one part.
You're always localized on one
and
bit.
While the other part exists, you can't.
Yeah. So they would say it's a probability of, I guess it's a probability, things are always something, so the probability in quantum mechanics is a probability of ignorance. There are other branches which are real, but unknown to you, but the values are unknown to you, and so when you assign these probabilities, you're thinking of it as a probability of something which exists, though is unknown to you.
Okay.
And so, yeah.
I don't like it.
I'm kind of making, I don't think that way, that's not the way that I think about it, and so I don't want to, I'm probably not saying things the way that they would want me to say it, so I'm hesitant to say too many words because I haven't forced myself to think that way, so one of these times I will think like a many worlds theory person just to see how things work out. Okay. This is what, so the question is, this collapse of the wave function. I don't like to use that language, and I think, I try to avoid it when I'm talking about things, but it does come up. I think of it personally as a reassignment of probabilities, like you're updating your probabilities, there are two shoes in a dark closet, or I've got my eyes closed for whatever reason, and I decide I'm going to get my shoes on without looking. I don't know. And before I reach in and pull a shoe out, it's 50-50. And then I reach in, I pull it, I make a measurement, I feel the shoe, and now instead of saying before I make the measurement, I would have said, well, it's only 50% that I'm going to get the right shoe. After I pull it out and I feel it, I say, well, it's 100% that I'm going to get the right shoe in my hand. So I think of it as an updating of probability.
That makes more sense.
Okay, but then one of the questions is, so another one, Schrodinger wanted to view this state vector, or in his language, the wave function that corresponds to it, but whatever, as a physical wave, like a water wave. It's real, like not real like complex numbers, I mean real like not a figment of your imagination, like it really is something in nature, in which case this would represent kind of a physical, a process on physical things, like a car can move and evolve and go down the road, that's a physical process the car can undergo. He would want to say this is like a water wave, and then you have to think of this as a real process. So a lot of these paradoxes, you have to, so every way of slicing it is you're going to run into something counterintuitive. You kind of have to pick your choice or your poison and then just kind of make your choice and I guess live with it. So, all right. Einstein, if you go back to the Solvay conference, I forget which one.
That one?
Yeah, the one on the wall. Is it that one? No, it's not that one. Hold on, is Dirac in that one?
Thought so, is it?
Yes, Dirac's in that one, so not that one, I think. The one that Dirac, I think it's the one Dirac did, he was too young, he wasn't invited, he wasn't famous then. I think it's kind of the first one where Bohr and Einstein were going back and forth. Maybe Dirac was there, but I don't think so. Well, I think it's Einstein's, the first objection he had, Einstein didn't present at the conference, but he kind of was asking questions after people gave presentations. And so Bohr didn't present either officially, but he wasn't going to, and then he was asked to kind of present, I think. And he had been giving talks, and he'd just given a talk at Lake Como. Cuomo? I think Como. Anyway, and somewhere in there, I don't know if it was during that or maybe it was just during the discussions, but Einstein asked a question about basically, I won't get it right, you send in, I think you just have one slit starting out with. You send in particles, they go through one slit, and the wave function, so when you're not making a measurement, we also, let me time out. Let me finish my summary and then we'll talk about this. I've got to get through that. All right, so this is a collapsed particle. This is the process of measurement. It's supposed to collapse this. This is one way that systems can evolve, how they evolve under measurement. When they're not being measured, when they're not being measured, so when they're the no measurement, when they're not being measurement, then the probabilities update, the states, we'd say the states evolve smoothly with the Schrodinger equation. Okay, and it doesn't matter, and what this, it's a differential equation, at least in non-relativistic quantum mechanics. It's the Schrodinger equation. There's some relativistic version that leads to quantum field theory, but there's some sort of smooth flow of how the probabilities, the correlations with experiments update, and what it says is I times Planck's constant times the time partial derivative of the state psi equals some matrix called the Hamiltonian matrix, or actually I should just say operator. It is a Hamiltonian operator acting on psi. And when you rewrite this in position space, you can rewrite it as a differential equation, and it's the sort of thing you learn about differential equations, or it's really a partial differential equations typically, but okay, it's just a ramped up version of what you've learned in the first couple of years of undergraduate studies. Okay, so this is norm. When you don't mess around with it, it just evolves, and turns out this looks like waves. But it's like waves, but these are complex waves. So let's insert complex waves, right? And so that's how Schrodinger. So what Schrodinger wanted to think is, no, these really are like water waves, when smoothly evolving in time, and very various interference patterns are just ripples in this wave. Okay, so now let's come back to what Einstein wanted to say, even in the Solvay conference. Well, he had the situation where you imagine you send in a particle or a beam of light or whatever, and you threw a pinhole, and then you pass through, and then you just solve the Schrodinger equation. Well, you know what's going to happen. It's like a spillway at a dam. The minute it leaves the spillway, it just goes out in waves, right? So I'm plotting wave fronts or crests, but they kind of have a circular character to it. And then there's a screen over here, let's say, representing the place where we're going to make a measurement. And what we find is that it's here, or here, or here, or here, or here. But it's only, when you measure it, its position, it's only found to be in one place, even though this wave was spread out. And what he was basically saying is, okay, so that means that when it interacts with this, kind of randomly, the wave function is now, instead of being a curve, instantly it localizes, concentrated here, 0 there. So what he was saying is, if you're standing over here, I'm probably putting words in his mouth, I'm not saying it as sophisticated as in a sophisticated way like he would. But the idea is, this person would have said, well, if you kind of were over here, you'd say, well, it's one of these round waves, round waves, round waves, round waves, and then immediately this interaction over here caused your wave to collapse. Well, this could be on Jupiter, and it's instantaneous. So it looks like you've got this instantaneous action at a distance sort of thing going on, which looks like it violates relativity. And so that was one of his first criticisms, and that's we're going to come back to that with the EPR paradox. So to understand that, Einstein very clearly was, I think, at that time, thinking of these not as sort of vectors encoding correlations with measurements. He's thinking about this as a real wave, and saying that this is a real wave that is dynamically going from this situation to this situation, and it is an element of reality. And so that I think it's important to kind of understand. I think that's where Einstein was starting when he started to try to poke holes in these things. Whereas Bohr and Heisenberg and Dirac and Pauli and Born and Jordan, they didn't think of the state vectors as elements of reality. They thought of them as somehow encoding our knowledge at a given time. So our best ability to make a prediction. Right? And so you have to keep, I think that's the heart of a lot of this. Are these things real? Or are they really just, in the sense that they represent an element of reality? Or are these just our best, the best descriptions statistically that we can make? Okay, so we went through superposition principle, we went through vectors, probabilities. There's one other thing I wanted to make a connection with, which is operators. I used one there, the Hamiltonian operator. I just want to kind of tie in with what Emily went through the last time. So we've got these state vectors. They can be acted upon, and I guess I've got in mind here, you can even manipulate them without performing a measurement, so kind of in the way that we could pass spinning particles through a Stern-Gerlach experiment, but not actually make a measurement. So intermediate, you can kind of, I don't want to get too far into that, because you guys are all going to take quantum mechanics officially and learn how to do all this stuff. But the point, it still stands that you can interact with systems, just like you can let them just freely evolve. That's a way of interacting with them, I suppose, too. And such interactions, which are smooth interactions, are non-measurement interactions, those are described by transformations. Just, you start with one vector and you end up with another vector. They're described by, we call them operators, which are just maps from vectors to vectors. And then in any given, you pick a basis, and you try to represent your vector concretely. Well, when you make that choice, turns out then you're going to come up with a specific representation of these operators, and then it's called a matrix. So the matrix is a representation of the abstract operator. If you don't choose coordinates, you talk about operators. When you go and choose a set of coordinates, a basic set of basis vectors, then you can write down something explicit in front of you, and then that's a matrix, is how you organize the data. So sort of a hierarchy in terms of abstraction, but okay. So operators do that. It turns out that there are some operators which are special, and in the sense that they represent possible outcomes of experiments, classical numbers, things that could possibly be amplified up to be measured. And we know that the numbers that we get out of real experiments are always real numbers, equivocating between the notion of real there. And so therefore you need special operators. It turns out you want to use their eigenvalues, and you need special operators where the eigenvalues are real, and those are called Hermitian operators. And so, what I will say is macroscopic observables, not even macroscopic, just call them observables. They don't have, spin's not macroscopic. Wow, whatever. So we'll just say observables correspond to Hermitian operators. Okay? Hermitian operators, so an operator is Hermitian if the operator equals the Hermitian conjugate. And what that really means is, so put that in parentheses, that means you take the operator, or in matrix language, when you write it out, choose a basis, write it out. What it means is if you take the complex conjugate of every entry and take the transpose. So you swap rows and columns. They're equal. Okay? So that is enough to ensure that the eigenvalues of this operator are real. And so there are other operators, but for some reason, those operators don't describe results of experiments we can perform. Somehow they're not amplifiable. That's how we want to say that.
So even if it has real eigenvalues, if it's not Hermitian, it's...
If it has real eigenvalues, it'll be Hermitian. Yeah.
All the time?
Well, I don't want to get into, if it's a finite dimensional vector space, if it's infinite dimensional vector space, then you gotta think harder. I don't want to, Hermitian, real, in practice, yes. I don't want to get into, I don't quibble on pathological examples. Yes. Let me think, can I? I think the answer is yes, though. The problem, as I'm thinking about it, is, so for finite matrices, the eigenspace of these operators will be, the eigenvectors are complete form a complete basis. So the eigenvectors of these things are linearly independent, and so therefore that you can use them as a basis. That's what when I write something like this, what I really mean as a basis vector, I'm saying there's some observable spin in the z direction who has this eigenvector, and there's another eigenvector minus z, and that's it. Those are the two eigenvectors of spin z, and because it's a finite dimensional vector space, and they're then these are complete sets, and you can use them as the basis vector for any other state. Okay. Mm-hmm. Now, for an infinite dimensional set, then it's more complicated to show that the eigenvectors of the Hermitian operator are complete, I think.
But it doesn't matter since physically everything's going to be finite.
You know, it's like everything in when you're using, as a physicist, when you're using math, it doesn't matter unless it matters.
It's a mathematician's problem.
Unless it's yours. Rather than proving from the outset that it's going to always work, I think the more productive route is usually to guess and check. And basically you make reasonable assumptions, work it out, and if it stays unpathological, unsingular, then you're okay. But sometimes you run into a place where you get screwy answers like 0 = 1, and you realize, oh, I forgot to include these states, and apparently in that case it didn't matter. But with experience, you kind of get a feel for when you're going to have to worry or not. Worry about it when you come to it rather than... Because if you worry about all the potential pitfalls before you get there, you never get started. So, all right. Hermitian operators, that's how it goes. And then those are, Hermitian operators are the observables. They're eigenvalues. So like if I had an operator, like momentum is an operator. Sometimes to remind us it's an operator, we put a hat on it. That doesn't mean unit vector, it means operator now. And then I can have a state P. So capital P, this P with a hat represents the operator. This is a vector indicating a specific outcome correlated with it. So I would say, little p here is it's a scalar, a number. Okay, so this vector is an eigenvector of p, comes back proportional to itself, and the constant proportionality is the eigenvalue. And by an abuse of notation, we label the eigenvectors by their corresponding eigenvalues almost all the time in physics. In math, it's not always done that way. And basically, you can think about the set of all possible eigenvectors as a basis for the space of all states. So you say they are complete. Okay, now, so then the algorithm we have, so we've talked about, given a state psi, the probability of finding momentum value p when you make a measurement is, so the probability of finding p given psi, we said was p with psi magnitude squared. That's the probability of finding momentum p given that you started with state psi. And then if you think about this, if you were to try to find an average value for the observable p hat, well, you would say, you would sum over all possible outcomes weighted by the relative probabilities. So you'd say, given a state psi, you'd say, that's summing over p. Really, it's probably an integral because momentum is continuous typically. The possible value times p with psi, the probability. But it turns out, and Emily showed this last time, you can rearrange this, and it turns out this is nothing other than just simply taking the original state psi, taking the matrix, sandwiching the operator between the original broad ket. It's the same thing. And so this is the average value of momentum, can be computed, given a state prepared in psi, in a condition psi, you can find the average value of this observable by simply sandwiching the operator, or matrix if you want to be concrete, between the two states. And this is kind of the recipe for how you, how we get probabilities, but also then how you just compute average values of certain outcomes. Okay, what's the average value of momentum? What's the typical or average value of position? You would replace P with X as an operator and work it out. Emily worked through some examples with spin, doing all those things. So that's kind of our quantum algorithm, kind of hopefully pulling together all the little bits from what we've seen, thinking about kind of 1 degree of freedom at a time. All right. In the next video, I'm going to talk about how do you kind of ramp this up to talk about something with 2 degrees of freedom at a time. So a particle could have momentum and spin. So it's this, but we're going to build on top of this a little bit. And then once you can do that, then we'll interpret basically the same structure as 2 particles, which happen, 2 separate particles, or 2 separate systems that that exist at the same time and maybe are even at different positions. And how would you sort of describe that? And that'll lead us to the EPR paradox. All right, so I'm sorry, this got a little long-winded, but that's kind of how everything we've gone through pulls together.